to the weather we know. And yet, sprites are tethered to the planet's electrical heartbeat, intimately linked to storm systems far below. Sprites may appear chaotic, but they reveal a hidden structure in Earth's global electric circuit. When a thunderstorm releases a massive bolt of positive lightning, carrying more charge and traveling farther than its negative counterpart, it creates an electric imbalance in the ionosphere. The atmosphere responds like a stretched membrane snapping back into place, and a sprite erupts to restore equilibrium. This is not lightning as we know it, this is a plasma event, an electric bloom, a brief conversation between sky and space. What's extraordinary is that sprites might not be unique to Earth. Similar transient luminous events have been hinted at in Jupiter's and Saturn's atmospheres, suggesting that these ghostly flashes could be a common feature of planetary weather systems across the solar system. Studying them might give us clues not only about atmospheric electricity but also about habitability, radiation dynamics, and how energy moves vertically through atmospheres. They're notoriously hard to observe, too high for most other instruments, too fleeting for the naked eye. But high-speed cameras, satellites, and even citizen scientists with low-light video gear have begun to pull sprites from the margins of mystery. Networks like the International Space Station's Lightning Imaging Sensor and the Japanese ISS instrument ASIM have captured their ghost-like geometries from orbit, allowing researchers to trace their timing, triggers, and altitude profiles with unprecedented clarity. And the more we study them, the stranger they appear. Sometimes, a sprite splits into dozens of parallel strands, cascading like an electric waterfall. Other times, it blooms into a mushroom-shaped burst with curling tendrils that pulse like a heartbeat. There are even rarer cousins, elves, blue jets, trolls, and goblins, each a flickering signature of electromagnetic energy breaking loose from the constraints of normal weather. Sprites remind us that the sky above is not just a passive canvas, but an active layer of electrically charged matter. Their brief, silent dances tell us that storms are not confined to clouds and rain but reach into the edge of space, connecting the troposphere, stratosphere, and mesosphere in electric conversation. The atmosphere is not a collection of isolated layers, but a continuum, a breathing, pulsing system whose patterns we are only beginning to decipher. They are delicate and colossal, ephemeral yet ancient, and their study draws us closer not just to understanding storms, but to understanding the boundary between Earth and space, a region where physics dances in plasma and silence. As technology evolves, so too does our ability to glimpse these fleeting phenomena with greater clarity. Ground-based observatories now use ultra-sensitive photometers and fast-frame imaging systems to dissect sprites frame by frame, revealing microstructures within the red filaments, subtleties that were previously lost in the blur of time. What seemed like simple tendrils of light are now understood to be composed of thousands of individual streamers, each a micro-discharge propagating through tenuous air with lightning-fast acceleration. These streamers, measuring mere meters in width but traveling at speeds approaching 1/10 the speed of light, exhibit behavior more familiar to laboratory plasma physics than to meteorology. They seem to pulse and bifurcate, forming clusters registers and branches like neurons firing in the brain of the sky. It's here, in this intersection of plasma physics and atmospheric dynamics, that sprites defy easy classification. They are part meteorology, part electromagnetism, part cosmic sculpture. What makes the gigantic red sprite even more captivating is its role as an emissary, an ambassador between the terrestrial and the celestial. When you see a sprite, if you're lucky enough, you're not witnessing a lightning bolt in the conventional sense, but the atmosphere's reaction to a sudden electrical demand from space. It's as if the sky briefly becomes a conductor, transmitting energy upward to rebalance a system stretched by the fury of storms. Each sprite, in its flash, is also a data point in Earth's global electric circuit, a planet-wide system of charge flow between the surface, clouds, and the ionosphere. Thunderstorms act as batteries, pumping charge upward, while sprites and their kin serve as relief valves for extreme events. Understanding this circuit is vital not just for atmospheric science, but for comprehending how space weather interacts with our planet, influencing GPS, satellites, and even the health of astronauts. There is also a poetic tension in the way sprites remain at the edge of visibility, too high for most clouds, too low for auroras, too fast for casual observation. They dwell in the mesosphere, often called the ignorosphere for how little we have studied it. Yet here, in this neglected altitude, lies a crucible of dynamic forces, radiation belts, electric fields, plasma waves, that ripple and shimmer, waiting for the right trigger to ignite a sprite. As research expands, questions multiply. Why do sprites favor certain types of storms? What determines their shape? Why some form as simple vertical columns and others as sprawling jellyfish? Can we use them to remotely probe atmospheric conditions without balloons or rockets? And perhaps most intriguingly, lasting traces in the upper atmosphere, ionization trails, chemical shifts, or even electromagnetic echoes that ripple across regions we have yet to detect. From mountaintops and space stations, researchers continue to listen, to watch, and to wait. Every sprite recorded in a cosmic diary, in words but we study or they whisper we lives, deep and upward in the consider intentions, and say, often them radio that just very low frequency ion charts. In this, interestingly, some researchers have proposed that sprites may even have subtle effects on atmospheric chemistry. The intense electrical fields and localized ionization could, in theory, contribute to the formation or destruction of transient compounds like nitric oxide or ozone in the upper atmosphere. While these effects are likely to be minor compared to global processes, they serve as yet another example of how dynamic and alive our atmosphere truly is, even in layers once thought inert and passive. But sprites are not merely the concern of physicists and atmospheric chemists. Artists, poets, and skywatchers have begun to embrace them as symbols of something deeper, a reminder that even in the most storm-tossed environments, beauty can arise from chaos, structure from turbulence, and light from hidden tension. Capturing a sprite on film has become a kind of pilgrimage for astrophotographers, who must wait in darkness near thunderstorms, with specialized cameras trained toward the invisible, hoping for a millisecond of wonder. And sometimes, a single frame contains an entire cathedral of light, a cathedral built from arcs, streamers, and spires that reach upward like prayers from the earth to the stars. From a philosophical point of view, sprites blur boundaries. They are liminal beings, inhabiting the threshold between weather and space, matter and plasma, science and myth. Their behavior is rooted in quantum-level particle collisions and macro-scale electric fields, yet the form they take resembles the branches of a tree, the neurons of a mind, the roots of some inverted lightning-born forest growing down from the edge of the void. In that sense, sprites are metaphors for emergence, complex patterns arising from the interplay of simple laws, flashing into existence with elegance and then dissolving just as quickly. They also challenge our sensory expectations. Lightning roars and cracks across the sky, sprites do not. They are utterly silent to human ears. You may see one and hear nothing. And that silence makes them flee, like a secret performed in another language. You must translate their meaning through instruments and physics, but you feel it through all. This quiet, momentary light can an invisible realm of forces always have perception. In that instant of red fire above the storm, the veil between Earth and space lifts. The planet breathes upward, and the heavens answer, not with thunder, but with flame. Physically, sprites emerge from the interplay of three critical systems, from below, the ionosphere above, and the mesospheric medium in between. When a large positive cloud-to-ground, (cg), lightning discharge occurs, typically carrying currents of tens of kiloamperes, it removes a vast quantity of charge from the cloud top. This sudden shift in the electric field propagates upbeat of light, disturbing the quasi-electrostatic field between the thundercloud and the lower ionosphere. This altered critical breakdown threshold in the mesosphere, where air density is sufficiently low to allow electrons to accelerate and multiply via avalanche ionization. The reduced neutral density at these altitudes increases the reduced electric field, E/N, a crucial parameter describing how efficiently electrons gain energy from the field relative to how often they collide with neutral molecules. At around 70 to 85 kilometers altitude, this ratio becomes optimal for triggering streamer formation, the slender plasma filaments that constitute the sprite structure. Streamer theory, borrowed from high-voltage laboratory discharges, explains much of what we observe. Streamers are self-propagating plasma channels that advance via electron multiplication at their tips. In the sprite context, upward and downward moving streamers form in clusters, sometimes with hundreds developing in parallel, leading to the familiar caret and column shapes seen in high-speed images. Laboratory simulations and fluid models show that these streamers propagate at velocities ranging from 10 to 10 cm/s and require background electric fields of several hundreds of volts per centimeter in the rarefied upper atmosphere. Interestingly, sprite streamers are cold plasmas. Unlike lightning channels, where temperatures can reach 30,000 K, the electron temperature in sprites may only be a few electron volts. 1 eV is almost equal to 11,600 K, and the ion and neutral temperatures remain close to ambient. The energy is concentrated in a small fraction of electrons, which gain sufficient velocity to ionize and excite atmospheric molecules, mostly nitrogen. The characteristic red light of sprites comes from the first positive band system of molecular nitrogen, N21P, emitting strongly around 670 to 800 nanometers, with additional blue-violet contribution tendrils. Studies using time microscopy have resolved sub-millisecond transitions between excited states, confirming that sprites evolve through a series of short-lived molecular interactions. The lifetime of the N21P state is on the order of nanoseconds, but because different streamer branches ignite sequentially, the whole is up to 10 to 20 milliseconds. Sophisticated modeling using the Poisson of the lowest absorption. When a sprite occurs, it modifies the local electron density, creating transient ionospheric holes and perturbed regions detectable via VLF transmitter signals. This allows scientists to indirectly map the conductivity profile of the upper atmosphere and understand how space weather and solar activity modulate its behavior. Another scientific frontier involves the interaction between sprites and gravity waves, oscillations in atmospheric density and pressure generated by storms, mountain ranges, or jet streams. Gravity waves can modulate the neutral background density in the mesosphere, influencing where and when sprites can form. Some models even suggest that gravity waves can precondition regions of the sky, making them more or less receptive to electrical breakdown, effectively acting as invisible sculptors of sprite geometry. In satellite data, sprites often appear in concert with other transient luminous events, TLEs, such as blue jets, conical discharges erupting from thundercloud tops, and ELVs, rapidly expanding rings of optical emission produced by electromagnetic pulses, EMPs, that travel laterally at the speed of light. These TLEs occur at different altitudes, and together they form a vertical and thermospherical coupling. Through these studies, we've begun to appreciate that sprites are not isolated events but are embedded in a complex electrodynamic ecosystem linking ground-level meteorology to ionospheric chemistry and even magnetospheric dynamics. The global electric circuit, once a theoretical abstraction, now takes on physical clarity through the lens of sprites, revealing that every thunderstorm is not just local weather but a node in a planetary-scale electrical network. Laboratory experiments have become a powerful tool in advancing our understanding of sprite physics. Although we cannot recreate a full-scale sprite in the lab due to size and pressure differences, controlled experiments in low-pressure chambers using pulsed high-voltage systems have replicated the essential conditions of sprite streamer formation. These experiments often use needle plane or point plane electrode geometries to simulate the intense local electric fields that form at the streamer tip, and they employ nitrogen-oxygen mixtures at pressures equivalent to the mesosphere, 0.1 to 1 torr. One key result from laboratory analogs is the validation of streamer scaling laws. According to similarity principles, the behavior of streamers, velocity, diameter, branching frequency, scales with the reduced electric field, E/N, meaning we can study mesospheric discharges by appropriately scaling down pressure and adjusting the driving voltage. Experiments have confirmed that streamer heads in sprites propagate due to photoionization, where UV photons emitted from excited nitrogen molecules ahead of the streamer pre-ionize the medium, enabling continued growth in a low-density atmosphere. This non-local process is essential for sprite development, as it allows the plasma to advance into regions with insufficient background ionization. Computational models complement these experiments, using fluid, hybrid, and particle-in-cell (PIC) approaches to simulate sprite initiation and streamer propagation. Fluid models solve the coupled equations of motion for electrons and ions, along with Poisson's equation for electric potential, under mesospheric conditions. These models reveal instabilities at the streamer head, branching mechanisms, and charge deposition patterns. More advanced PIC simulations track individual particles, capturing kinetic effects such as electron energy distribution, secondary avalanches, and sheath dynamics. On a larger scale, global sprite climatology is now being mapped with satellite constellations such as NOAA's GOES-R, ESA's ASIM aboard the ISS, and the Chinese LAS/GLM sensors, which can detect lightning flashes and their associated optical transients. These data sets have enabled the correlation of sprite occurrence with mesoscale convective systems, MCSs, showing that sprites are more common over continental land masses, particularly in mid-latitude regions during summer. The most prolific sprite-producing storms are usually quasi-linear convective systems, QLCS, with sustained, long-duration lightning activity and strong charge separation. From these global datasets, researchers have derived statistical properties of sprites, their typical delay after apparent lightning stroke, 10-50 ms, altitude range, 50 to 90 kilometers, horizontal span, 10 to 50 kilometers, and optical intensity, up to several megarayleigh. A megarayleigh is an astronomical unit of brightness, and a sprite can briefly outshine the night sky background by orders of magnitude, though not enough to be easily seen without equipment. The connection between sprites and the Schumann resonances, natural resonant frequencies of Earth's electromagnetic cavity, about 7.8, 14, and 20 Hz, is another frontier of study. Some researchers propose that large-scale TLE activity modulates global resonance amplitudes, subtly altering the electromagnetic environment for days or weeks after large thunderstorm outbreaks. This connects sprites to broader questions in geophysics, such as the coupling of the lithosphere, atmosphere, ionosphere system and the potential for electromagnetic precursors to seismic events. There's even emerging interest in the biological implications of sprites and related phenomena. Though far above commercial flight altitudes, the electromagnetic pulses associated with sprites and TLEs could affect the local radiation environment in the mesosphere and lower thermosphere. Some theoretical work suggests that cosmic ray particles interacting with sprite-related fields may produce runaway electron avalanches or high-energy X-ray and gamma-ray emissions, part of what are now called terrestrial gamma-ray flashes, TGFs. These TGFs, detected by missions like NASA's Fermi Gamma-Ray Space Telescope, suggest that thunderstorms and associated phenomena like sprites may be among the most energetic natural particle accelerators on Earth. This positions sprites not only as spectacular optical displays, but also as critical agents in high-energy atmospheric physics. Their study overlaps with astrophysics, radiation physics, and even quantum electrodynamics. The Earth, it turns out, is not just a passive receiver of cosmic energy, it generates bursts of relativistic particles in its own sky, using thunderstorms as launch pads and sprites as signals. Planetary analogues of sprites open a new and thrilling dimension in the study of atmospheric electricity. If gigantic red sprites are the Earth's way of discharging extreme electrical tension between tropospheric storms and the ionosphere, then it is plausible that similar mechanisms may operate on other planets, especially those with thick atmospheres, convective cloud systems, and strong magnetic fields. Jupiter, for example, has the most powerful thunderstorms in the solar system. Observations by the Juno spacecraft have confirmed lightning at depths far below the ammonia cloud decks, with bolts potentially thousands of times more energetic than those on Earth. Juno's ultraviolet spectrometer has recorded flashes of light at altitudes far above these storm regions, flashes that resemble the hallmarks of transient luminous events, TLEs. These include rapid, upward propagating discharges with a spectral signature compatible with excited hydrogen, suggesting the presence of Jovian analogues to sprites and elves. Unlike Earth, where sprites arise primarily from molecular nitrogen emissions, Jupiter's upper atmosphere is dominated by hydrogen and helium, so any Jovian sprite would likely appear as a blue or ultraviolet flash due to the different emission spectra of atomic and molecular hydrogen. This offers a new challenge: how to adapt Earth-based detection techniques, designed around nitrogen red emissions, to find sprite-like events on gas giants with different chemistries and atmospheric pressures. Saturn, too, exhibits massive electrical activity. The Cassini mission detected persistent lightning storms in its equatorial belts, with flashes powerful enough to be seen from orbit for weeks at a time. While direct evidence for sprites on Saturn remains elusive, models suggest that the enormous vertical extent of its atmosphere and ionosphere could allow for massive high-altitude discharges, possibly dwarfing Earth sprites in size and energy. The ionospheric boundary on Saturn lies far above its cloud tops, offering an immense electric field potential and a large spark gap in which TLEs might form. Venus presents a different, more enigmatic case. Though its lightning is not yet definitively confirmed, electromagnetic anomalies recorded by Soviet Venera and later by ESA's Venus Express suggest possible thunderstorm activity within its thick sulfuric acid cloud layers. If sprites do exist on Venus, they would need to propagate through an atmosphere dominated by CO2, with a dense and thermally layered stratification. Modeling shows that such discharges might produce a greenish or yellowish light due to emissions from CO2 and atomic oxygen, although the high background brightness of the Venusian atmosphere would make detection extremely difficult. Beyond our solar system, the study of sprites may even intersect with exoplanet research. Brown dwarfs, objects between the mass of a planet and a star, show signs of powerful atmospheric storms and radio emissions that may be consistent with lightning and TLE-like phenomena. If sprites exist there, they may occur in atmospheres composed of exotic molecules such as silicates, metals, or ammonia, emitting light in entirely unfamiliar spectral regions. Detecting such events could become a new method for remote sensing of alien atmospheres. Back on Earth, one of the most fascinating links between sprites and high-energy physics comes from their association with relativistic runaway electron avalanches, REAs. Under strong electric fields in thunderstorms, electrons can be accelerated to near light speed if they avoid enough collisions. These high-energy electrons can produce X-rays and gamma rays as they collide with air molecules. This is the mechanism behind terrestrial gamma-ray flashes, TGFs, which were first discovered by NASA's BATS instrument in the 1990s. Sprites appear to correlate with TGFs in certain cases. Some models propose that the electric fields above thunderstorms, especially those that generate sprites, may serve as secondary acceleration zones for upward-moving relativistic particles. In this sense, sprites might serve as beacons not just of electrical breakdown but of high-energy particle acceleration, a role previously thought exclusive to astrophysical environments like pulsars and black hole jets. There is even speculation that such particle showers could have influenced Earth's atmospheric chemistry over geological timescales. During periods of intense storm activity or geomagnetic variation, the increased flux of gamma rays and secondary particles from thunderstorm-induced discharges could alter the production rates of nitrates and contribute to transient climatic effects. Although speculative, this idea opens a new interdisciplinary frontier connecting atmospheric electricity, climate science, and geochemistry. Sprites, therefore, sit at the nexus of many disciplines: electrodynamics, atmospheric science, quantum physics, astrophysics, and even planetary science.